A very good morning to everybody. This is Ajeet Manna, and I am going to cover all the syllabus of class 11th and 12th in this channel. So stay tuned to me. And in this lecture, we are going to start chapter first of class 12th maths, that is relation and function. So, what is relation and function? As you have already learned in class 11th, that relation is a set which define a relation between two sets. Here is set A and here is set B. A is having some element and B is having some element. Then relation is the set of another relation is another set which is having element from both these set with having some certain conditions. For example, I had defined a relation like this and also tell you that A belongs to element A, set A, and small b element belongs to set B. Then how will this relation came into the picture? So if we take first element of this set and put it here, then b plus 1, b 2 plus 1 3, 3 will come across here, A will go to this set, so 3 comma 2. Then is it possible to write any other element? Suppose we put 3 here, so 4 is not present, so this is the end of our relation. So whatever I have described here is the pictorial representation of a relation, and this is the set builder form to represent anything, and this is the roster form of representing a relation. Okay, now recall that the notion of relation and function, domain, codomain, and range introduced in class 11th. In class 11th, you have studied about a little bit about relation and function, domain, codomain, and range. These all the topics have been covered in class 11th, and what we are going to study in this class 12 today, among with these different types of specific real valued function and their graph. We have also studied about the various real valued functions and their graph. For example, if you draw the y equals to x graph, this will look like this. So all the relation in function, this is basically function. Here sometimes y is written as fx is equals to x, so y is also, so this is the graph of fx in x-axis and y-axis. This is the graph of fx. Okay, now the concept of a relation in mathematics have been drawn from the meaning of relation in the English language, according to which, what is the meaning of relation in English language? Two objects or quantities are related to each other with their recognizable connection or link between the two quantities. That relation is relating to object. Okay, what is relation? Relation is relating to object by their recognizable connectivity or connection. Suppose I am relating you with your dad as a relation of father. So this is where the relation comes into the picture, that relating to objects or quantities, objects with their recognizable connection, recognizable connection. This is what called as relation. Okay, so here some few examples are listed. Let A be the set of student of class 12th of your school. A be the set of student of class 12th of school. Student of class 12th of your school. Okay. Now B be the set of student of class 11th of your school. B be the set of student of class 11th of your school. Then some of the examples may be some of the examples of relation. There are many relations which you can form when you have having two sets. Okay. So set A is saying that A comma B such that belongs to A cross B. A cross B is the relation. Okay, A is the brother of B and he is the sister. So these are the few examples of relations which you can make from the two sets. Okay, in this chapter we will study different types of relation and function. So first we will cover the different types of relation and then we will cover the different types of functions. Composition of functions. Composition of function means adding two functions, subtracting two functions. These are the composition of two functions. Invertible function, we will study about invertible function and the binary operations between the various types of function. Okay, so coming to our very first topic, this is types of relation. Okay, so coming to video 1, the relation R in set A is called an empty relation. So first the first type is the empty relation. If no element of A is related to any element of A. So if I am taking two sets, okay, set A and set A, and here some element, and I am giving a relation that A comma A belongs to A cross A such that A comma B. Okay, so B is equals to A square. So you will find nobody having this perfect square. Squaring 1 will be 1 but it's not present here. If this is 1 to 1, so squaring 2 is not present here, squaring 3 is not present here. So this is an example of empty set, that you will find no element in their relation. Relation is defined in such a way that you will find no element, then what you will call empty set. The empty set is written by the symbol 5. Okay, so R is equals to 5 will be the answer of this question. Coming to the second definition, the relation R in set A is called universal relation. Now what is a universal relation? If each element of A is related to A, that of A, R is equals to A cross. If each element of A is related to A, suppose I give 1, 2 and here 1, 2. A to A is the relation. 1 is related with this, and this also, and 2 is related to this and this also. So in relation you will get 1, 1, you will get 1, 2, you will get 2, 1, you will get 2, 2. So such types of relation in which each element of A is related to every element of A. One is related to this element and one is also related to this element. 2 is related to this element and 2 is also related to this element. So this is where, that is where we call it as universal relation. Now I am going to elaborate this two types with few examples. So what are the examples I'm going to discuss in this lecture today? So very first example is, let A be the set of all students of a boys school. So A be the set of all students of a boy school. So we are taking a boys school and we are considering all the students of them in set A, and R is given that A comma B such that A is sister of B. A is sister of B. So is since this is a boys school, so we have to define A to A relation. Okay, here all the students of boys school, here all the students of boys school. Can two boy can be the sister of each other? Tell me this one thing. So you will find none of the boy is having sister of other from the same school. So you will get here the empty set or the empty relation. Empty relation. So none of the boy will be the sister of another boy. So this is the solution for part A. In part B, they are giving us another relation saying that A comma B such that the difference between the height of A and B is less than 3 meter. So now you can consider all the elements of A, because the difference of two students of two height will be always less than 3 meter. So you will get all the element all the student in this set, A to B, A to C, A to D, dot 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 dot, dot. Then B to A, B to C, and B to B is also here. Okay, so A to A is also here, then B to B is also here. Means I'm considering all the students to be as A student, B student, C student, D student. I'm considering like this. Okay, A student, B student, C student, D student. So all these students are actually an element for us. So R dash is an universal relation. Universal relation. Because R dash is having all the students related to each other. A is also related to A, and A is also related to B, A is also related to C. Because the difference of the A to A is also less than 3, A to B is also less than 3, A to C is also less than 3. So we can consider all the elements of A to each other. Then we can consider B to A, B to B, B to C, B to D, C to A, C to B, C to C, C to D, D to A, D to B, D to C, D to D. Okay, that's why this relation is the universal relation. Now coming to the definition 3 of this chapter, after solving first example, the relation R in a set A is called reflexive. So what we will have to study here is a reflexive. If A comma A for every A belongs to A is present in this set. Okay, this is what we will have to consider in this coming definition. So what is reflexive? Reflexive is a type of relation which is having the same quantities like this, like 1 1, like 2 2, like 3 3, and so on. If you have a set having 1 2 3 only, then if the relation is having 1 1, 1 is also repeating with 1, 2 is also repeating with 2, 3 is also repeating with 3, then this set will be reflexive. Means if it has 4 then it also have to 4 comma 4. If 4 comma 4 is not present in the relation set, then this relation is not reflexive anymore. Okay, so this is reflexive. If you will have to get a comma a for every a belongs to set A. For every element belongs to set A, the pair will have to be in the relation. Then only the set will, this relation between the relation will be reflexive. And now coming to the second part is, if a comma b is there, then b comma a is also present in the relation. Okay, so for symmetric, suppose you have 1 comma 2 in the relation, then 2 comma 1 is also have to there. Suppose you have 3 comma 5 is there, 5 comma 3 will also have to there. So there is no, now there is compulsion actually. For all a1 a2 belongs to a, means for all element present here, the pair will not, the pair also have to be there, then and only this is symmetric. What do you mean by symmetric? Symmetric, when you stand in front of mirror, you see your face to be very much similar to each other. Your face is similar to you and you is similar to your face on the mirror. So that's why if 1 2 is there in the set, then 2 1 has to be there in the set, then it's symmetric. Now we will have to study about transitive. Transitive is the transitive deals with 3 elements in the set, a1 a2 and a3. Okay, so how uh, we will identify that the set is reflexive or not. Suppose ab is there, then you will have to bc here, then ca here. So if all the three loops are being completed in this relation, then it is transitive. How it will be transitive? Suppose 1 2 and 3 are in the set A. Okay, so in the relation 1 2, you will jump to 1 to 2, then you will jump to 2 to 3, then you will jump to 3 to again 1. Then it is called, this relation is called the transitive. So you learn about reflexive, if the same element will be in the relation. If symmetric, if the transpose elements are being there, 1 2 and 2 1 is there. And you learn about transitive. Transitive deals with 3 elements, a b c, and the fourth definition tells about the equivalence relation. Equivalence relation will have the all the 3 definition right there. Okay, all the 3 definitions means here that if a relation is symmetric, transitive and reflexive, all 3, then the set will be the equivalence relation. So for a relation to be equivalence, the set must be symmetric, reflexive and transitive. Now we will solve some example to better understand this. So let T be the set of all triangles in the plane. Okay. So T be the set of all triangles in a plane. So we consider all the triangles in the plane as T set, and R is saying that I will have only those triangles T1 T2 such that T1 is congruent to T2. I will have only those triangles which are congruent to each other. So if I consider to prove first to prove equivalence, you will have to prove reflexive, you will have to prove symmetric, you will have to prove transitive. So if you can prove all these three types of relation, then you can say that the set is the equivalence relation. Okay, so for a set to be reflexive, what we are for a set to be reflexive, it must be the same element, that is a comma a must be there. Okay, so I considered a triangle 1 1 1, and the same triangle I have again drawn here 1 1 1. This is T1 and this is T1. So is T1 is congruent to T1? Just tell me. Every triangle is congruent to itself, no doubt. If T1 is congruent to T2, T1, and then T2 is also congruent to T2 again. So what we are going to write here? We are going to write here that R is reflexive because every triangle is congruent to itself. Every triangle is congruent to itself. Yes, so that, okay, so what we are going to write here in the, that is T1 comma T1. T1 is congruent to T1, T2 is congruent to T2, T3 is congruent to T3, and so on. So this is why the relation R is reflexive. Now we will have to prove the symmetric part. So for a relation to be symmetric, the transpose of the element must be present in the set. So how we are going to prove this? We are going to prove this by considering two triangles 1 2 3 and another triangle 1 2 3. This is T1 and this is T2, and you are saying these triangles are congruent. If T1 is congruent to T2, then T2 is also congruent to T1. So this is why the relation R is symmetric here. R is symmetric because if T1 is congruent to T2, then T2 is also congruent to T1. So in the relation we write T1 T2, then T2 is also congruent to T1. Similarly, if T3 is congruent to T2, T4, then T4 is also congruent to T1, T3. So this is how this relation R is symmetric. Now we have to prove transitive. For a set to be transitive, there must be three triangles. So I'm again considering T1, T2 and another triangle here with 1, 2 and 3 side and naming it T3. So if this triangle is congruent to this and this triangle is congruent to this, then the third triangle is also congruent to this. So that's why this relation is transitive. R is transitive because if T1 is congruent to T2 and T2 congruent T3, then T3 is also congruent T1. So R is transitive because T1 T2 is present here, they are congruent. T2 T3 is present here, they are congruent. and T3 T1 is present here. They are congruent, and many more congruent triangles will be having a three circular loop in this. And since this relation is reflexive, symmetric and transitive, all the three phases, so it is an equivalence relation. Why equivalence? Because it is satisfying all the three criteria needed to be a relation for symmetric. Coming to our example number 3 of this session. So what we are giving having L be the set of all lines in a plane. Okay, L be the set of all lines in a plane. So a plane is here and different types of line are being drawn here. Okay. So these all are the lines. Naming line is L1, L2, L3, L4, L5 and so on. Okay. And now we will have to define, we have given a relation such that L1 comma L2, L1 is perpendicular to L2. L1 is perpendicular to L2. Now we have to show that the R is symmetric but neither reflexive nor transitive. Okay, so we will have to again solve all the three criteria here: reflexive, symmetric and transitive. Okay, so first we are solving for reflexive. So for reflexive, we draw a line L1 here. This is the plane and I have drawn a line L1. Will this line L1 will be perpendicular to itself? This is another line L1 looking similar, and will this line will be perpendicular to itself? No. So L1 comma L1 will not come in the relation. This is why the set is not reflexive. So what we are going to write here? We are going to write here R is not reflexive because L1 is not perpendicular to L1 itself for any L1 belongs to R. Now drawing for symmetric. For symmetric, we take another line L2 which is perpendicular to L1. Okay. So if L1 is perpendicular to L2, then L2 is perpendicular to L1. So if we write L1 comma L2 in the relation, then L2 comma L1 will also come in the relation. So this is symmetric because, so R is symmetric because if L1 is perpendicular to L2, then L2 is also perpendicular to L1. So we can have a relation in the relation L1 comma L2, L2 comma L1 and so on. So this is symmetric. Coming to solve the third part, transitive. So for set to be transitive, the RS will have to consider the three lines. Okay, so I'm considering L1. Okay, here L1, then drawing a line L2 such that L2 is perpendicular to L1, and drawing another line L3 which is L3 is perpendicular to L2. So you can see that L1 is perpendicular to L2, L2 is perpendicular to L3, but L3 is not perpendicular to L1. So the three cycle loop is not getting completed here in this relation they are giving us. So the L3 is not perpendicular to L1, so we get this set to be, this relation to be non-transitive. R is not transitive because L1 is perpendicular to L2, L2 is perpendicular to L3, but L3 is not perpendicular to L1. So we have proved that it is symmetric but not reflexive, not transitive. Coming to our fourth example, so that the relation R in the set 1 to 3 given by 1 2 2 3 2 3 is reflexive but neither symmetric nor transitive. So here we have a 1 2 3, another set 1 2 3, and they are giving us a relation where they are not giving the relation statement, but rather they are giving this relation in roster form. So for reflexive every element should be in the pair with each other. So 1 is with 1, 2 is with 2, 3 is with 3. Okay, so 1 is with 1, 2 is with 2, 3 is with 3, and only 3 elements are there. So this is reflexive because R is reflexive because 1 1 2 2 3 3 belongs to R for every, means for all the elements are being covered in the 3 pairs. Now if we come to symmetric part, symmetricity says that 1 has to be with 2 and 2 has to be with 1. So in this set 1 2 is present but 2 1 is not present, so 2 1 will also have to there. In this set 1 2 3, and then we have 3 2 will also have to there, and also 1 3 and 3 1 has to be there. So they are missing actually few elements, 3 1 and 1 3 is also have to there. So we are lacking this 4 element in the relation. That's why this R is not symmetric. Okay, R is not symmetric because 1 2 comma 2 3 belongs to R, but 2 1 comma 3 2 comma 1 3 comma 3 1 not belongs to R. Only then we can say that the pair is getting covered. So for every the definition which I have just written here, for every a1 a2 belongs to A, means for each element has to be cover the pair from the other element. Okay, now coming to transitive part. Transitive will say that if you are going from 1 to 2, then you will have to go 2 to 3, and then you will have to go 3 to 1. Okay, so is this is getting completed? Let me check. Okay, so in the relation they are given here, 1 is going with 2, 2 is going with 3, but 3 is not going with 1. So this one set is missing here. That's why this relation is not more any transitive. Okay, so R is again not transitive because 1 2 comma 2 3 belongs to R, but the third pair, which is 3 comma 1, does not belong to R. That's why the symmetricity, that's why the transitivity is not getting completed. Coming to the example number 5. In example number 5, we are giving a z, which is an integer set. Integer set. So we will consider first z set here and second z set here. Okay. To z we will have to define a relation. And what relation statement is saying? Relation statement is saying that I will have elements in pair a comma b such that 2 divides a minus b. Means we will have to first subtract the two elements and then we will have to divide it with 2. So this is our question. So I'll have to consider a lot of integers in the sequence, and then we will have to subtract these two elements and then we divide each other. So we will have to prove that this is an equivalence relation, and for equivalence it has to be reflexive, symmetric and transitive. So first I am proving here reflexive part. So what is reflexive? Basically the reflexive must have to 1 with 1, 2 with 2, 3 with 3, 4 with 4, 5 with 5. So is this is satisfying with this condition? So let me check. We'll have to subtract these two, 1 minus 1 and divide it with 2. 0 by 2 is 0. So we are getting our answer 2 minus 2. 2 minus 2 by 2, which is 0 by 2. We are getting our answer. So every element here is satisfying the relation criteria, that is the difference must be divisible by 2. And here what we are getting, we are able to divide, we are even able to divide the numbers without leaving any remainder. So what we are going to write, R is reflexive because 1 comma 1 comma 2 comma 2 dot 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 belongs to R. 1 comma 1. Now our second part is symmetric. Next part is our symmetric. So what has to be in the symmetric part? In the symmetric part you will have to be the reversing one. Suppose you're taking 2 comma 4, then 4 comma 2 must be there. If you're taking 5 comma 3, then 3 comma 5 must also be there. So these all elements must be there in a similar way. Now we are going to check these two conditions. So first we will subtract 2 minus 4 divided by 2. So what is 2 minus 4? 2 minus 4 is negative of 2 by 2, which cancelling with giving negative 1 result. So we are able to divide this difference with 2. That's why this 2 comma 4 is in the relation. Now we have to check 4 comma 2 with 2. Okay, so we're getting 2 by 2, which is able to 1. So we are able to again divide the difference with 2. So that's why this is in the relation set. So what we are going to write, R is symmetric because 2 comma 4 comma 4 comma 2 etc belongs to relation. these are present in the relation set. That's why the set relation is the symmetric. Now we'll have to prove about the transitive part of this. So what has to be there in the transitive part? So in the transitive part, suppose you taking 1 with 3, 1 with 4, 2 with 4, then 4 with 6. 6 has to be there with the 2. Means the 3 loop between the 3 numbers which are satisfying the criteria of the relation must be there in the loop. So let me check. Suppose I take 2 4 and 4 6, then 6 comma 2 will have also be satisfy this. So if I'm going to check this, then let me check. So now what we are going to do here is, okay, so coming back to our regular curriculum courses. Okay, so our next question is, if 2 comma 4 is there, so I'm going to subtract 2 with 4 and we are getting negative 2 by 2, getting negative 1 answer. 4 6 negative 2 by 2, we are getting negative 1 answer. 6 comma 2 and we are getting 4 by 2, we are getting 2 answer. So in all the three cases we are able to divide the relation, divide the difference of these two by 2. That's why this is transitive. R is transitive because one, because the 3 pair is being present here, because 2 comma 4 comma 4 comma 6 comma 6 comma 2 belongs to R. So since the relation is reflexive, symmetric and transitive, the relation is equivalence. Coming to the sixth example of this chapter, number 1, let R be the relation defined as a set A such that set A is having 1 2 3 4 5 6 7, and another set we will have to define 1 2 3 4 5 6 7. So this is set A and this is another set A, and they're saying the first relation as A comma B such that both A comma B and are either even or odd. Okay, so both A and B are either even or odd. Okay, so that it is equivalence relation. Okay, so what we are going to, if we are going to write in this relation in the roster form, this is the side builder form, means they're explaining it in. So if we are taking both odd like this, 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 one is with 5, one is with 3, one is with 5. So these are all the, I'm considering it as odd numbers. Okay, so 1 with 1, 2 with 2, 3 with 3, means that this is even to even, odd to odd. Okay, 1 with 3, 3 with 1. Okay, 1 with 5, 5 with 3, 1 with 5. So why it is reflexive? It is reflexive because it is having a same similar number. Like this is why it is reflexive. And 1 is 3, 1 with 3, 3 with 1. This is why it is symmetric. And why it is transitive? Transitive because 1 with 3, 3 with 5, and 5 with 1. All the three are being present here in the relation. That is why it is transitive also. Okay, so what is here? 1 with 3, 1 with 3, ठीक है, 1 2 3 हो गया. Then we have 3 with 5 and 5 with 1. These all are getting completing a circular loop. This is why it is transitive. Since this relation is reflexive, symmetric and transitive, that's why it is an equivalence relation. Equivalence relation. As I explained you writing the earlier question, you will have to also write the same question, the same pattern. I'm not writing here in this because there is the another part which we will have to solve it here once again. Okay, so we have solved till here. Now further, so that the elements of the subset 1 3 5 7 are related to other elements of the subsets but not elements related to the subset of this. Okay, now what we have to see, the elements of the subset. Now we have 1 3 5 7 are related to each other, are related, and the elements are related but is not related to each other but so in the earlier question they are explaining us that 1 3 5 7 is 1 3 5 7. These are odd, these are odd. So we are, according to the relation, we have just considered 1 to odd to odd only. Okay, all odd to all odd to odd. But and similarly we have related like this. Similarly 2 4 6, 2 4 6 we have considered odd, even to even. Okay, even to even. But we are not relating any odd element to any even element. That's why we are getting the said to be reflexive, symmetric and transitive. If we are going to relate even to odd, then we will break the rule of the relation and we will not get any element to be inside the relation defined by them. So this is the end of our class. Thanks for watching. Stay tuned with us.